Welcome to CSCI E78's Team 3A's case study of the connected car. In this study, we're going to talk about three uses of parking, traffic, and diagnostics. Welcome to the connected car parking is what we're going to discuss here. And definitely a connected car is a car with internet access and a wireless LAN. You see a little diagram of all the availability of connections in the car on this dashboard on the right. Now, this started in 1996 when we first started, the car company started with connections to an emergency call center connection. We can also have a current Bluetooth to smartphone connection, which is just a local connection with you and your car and your phone. If you connect it to the internet, you will have availability to a GPS, turn-by-turn directions. A BMW, for example, has the BMW Assist button in the car, and if you subscribe to that service, of course, you can press that automatically. Someone will assist you with anything you want in terms of turn-by-turn. Again, car manufacturers now include remote diagnostics, and your car service will call up and set up your appointment based on the fact that the car has communicated a need for a service call. So that is progression from 1996. Currently, we can connect to the internet for more information than just that basic, what might be termed basic information. Now we might be actively seeking out the local restaurant en route to my destination. We might actively seek out other valuable information like quick coffee drive-through, or navigate to find out where some other object or some destination is with respect to my designated location, my current location in the traffic that I'm in, and see if I can maybe change my navigation to that site before attempting to renegotiate traffic. And the car itself will negotiate that whole procedure. It will also find the best parking spot. So welcome to the connected car. So the purpose of the connected car's parking is to improve parking efficiency, especially when you have traffic congestion. And a scenario where that would probably be most relevant is when you have congested traffic and you have a time-sensitive situation. You're trying to get to your appointment on time, and you encounter accidents or road closures. Normally, we would try to scramble in our brain and try to use the GPS while keeping our eyes on the road to drive to calculate where our next maneuver would be. Should we sit in traffic and wait this out, or should we take an upcoming side street and circle around, or figure out how an alternate route might pan out? And a smart or a connected car would therefore create a scenario where it would get that information from the city's database on the road closure or the accident, calculate whether sitting and waiting it out or doing an alternate route would be the best option, and take that best option. This is most relevant in an unfamiliar territory, in an unfamiliar city or an area of the city. Suppose you've landed at the airport, you rent a car, and you're not familiar with the city at all, and you're trying to get to an appointment. You encounter different scenarios on the road to there, and you can solve the problem better with the information from the connected car and let it figure out how to get to the parking spot for you. So basically, the benefit would be parking is now a streamlined process. You have less idling, so you're saving fuel and time, and then you have less frustration. The advantage of a connected car parking is that it is faster. You have decreased frustration in finding a spot, and so you have saved fuel in locating, and you reduce stress in locating a parking spot where you have a failed attempt. A failed attempt is a parking attempt where the parking spot is taken once you arrive, or the parking spot has been allocated once you arrive to the spot, unbeknownst to you, to the owner of the company you're at, the staff of the company you're at, or maybe it's a short-term parking for immediate emergency type visitors. Whatever conditions might be applied to that particular spot you are seeking out might be information you only get after you arrive at the spot, whereas the connected car would know that that spot is not ideal for you. We have the infrastructure from the city where the sensors are placed in parking areas. So the vehicle is talking to that infrastructure communication. Now, INRIX is a company which has tried this out by using the ultrasonic sensors of the car, which we already have in current cars to sense our proximity in parking or backing. It tells you on the dashboard, it beeps when you're close within a certain amount of space to some object so that you know as you're backing that there's an object behind you, for example, and that's your ultrasonic sensor from the car. So you can use that to detect empty parking spaces while you're driving by. And the car connects to the internet through 4G or 5G, depending upon the technical architecture that that communication is based on, and sends that data to the cloud to compare with the existing parking database that the city has based on current information of parking spaces, and it can detect where it's empty, and it knows the size of your car and whether it can fit into it. So the smart infrastructure has sensors in the parking areas, and it communicates the car through a Zigbee network. That's how the technical architecture in a top level very simply is designed. In a connected car, the technology is changing while time's arrow in technology moves in one direction only. We've seen this with phones. Previously, we had phones which were only used for phoning someone, and you had to literally phone that number each time you wanted to use the phone. Now, we might be sitting in the car and calling out the person's name, and we connect with that person immediately. So inevitably, we will all be more connected in all the devices than previously. So the fact that we can build a city or a village based on a connected car technology is impressive in that it defeats the argument that too many cars can cause traffic congestion and inefficiency in transportation. One of the common issues that cities put up with, and even villages which have development projects, are coming across traffic issues with developers and local middle income participants or people who take part in these projects in the village. So this global issue can be a little bit addressed with this connected car because the traffic congestion would be alleviated by the intelligence and the machine learning of the car. And the inefficiency again would be reduced because of the connection. We do know that a connection issue or mathematics of the connection has to look at the traffic patterns and the parking issues and solve them. This is a multi-variable problem, which has as variables the available time you have to get to the appointment, the traffic pattern, the road conditions, and the parking is a function of how long you're going to park and the proximity to the destination and a convenient walking route. The machine learning can figure out if you parked across the street at a cheaper parking location, but you may not have enough time to walk across the street to get to your appointment. However, if you wanted to pay more for parking but get to your appointment on time, it can find you a more appropriate parking spot for that. So challenges to the increased use of connected car, basically anything with a connection has a hacking issue that has to be addressed. Privacy, security. Privacy, where is this information going? I'm sitting in traffic. Does the car company know I'm sitting in traffic at this particular spot? Does the city know that I'm sitting in traffic at this particular spot? How many people know this? And how many people knowing that am I comfortable with? Are there people that I don't want them to know this information? How about the public's faith in the system? Previously, when we flew on airplanes, we did not realize that the pilot would put the system in automatic pilot. We were quite content sitting there or sleeping and finding ourselves happy with the flight. Now we know that we're still sitting there. We still know that the automatic pilot has come on, but we are more confident in that system, in that we feel that the flight will still be safe. That's the kind of faith we need to have in the system if we are to let go of our authority on the connected car and have it make the decisions. Roland et al. In his book Designing Connected Products says connectivity is like the air that we breathe for many younger consumers. But what about the mature consumer whose familiarity with technology may still be that flip phone where they have to actually put in the number they're trying to dial? Maybe they're not as happy with a smartphone which has all the information about the latest news, or the closest coffee shop and how to get there, or walking pattern to their next destination. Maybe they just want to figure all of that out themselves because that's what they're used to, and they're not comfortable relinquishing that decision-making process to their phone.
In this part of our connected cars presentation, I would like to discuss optimizing traffic flow. As previously mentioned, a connected car is a vehicle offering one or more connected technologies. These can include telematics, some GPS-based navigation systems which both receive and transmit data, and possibly even some Bluetooth-connected mobile devices. Here I will consider a connected car to be a vehicle that collects and transmits data outside of the vehicle itself. Today, at least 1 in 5 vehicles can be considered to be connected cars. Manufacturer-installed systems such as OnStar, Intune, and Uconnect could be connected car enablers. First, I would like to consider the differences between driverless and connected cars. As we get closer to accepting the concept of the driverless car, we must first understand and implement the concept of the connected car. A connected car is usually connected via cellular radio signals to the public internet. It uses this internet to establish secure encrypted connections to other vehicles and devices. A connected car may communicate with traffic signals, traffic cameras, intersection loop detectors, traffic control centers, and other vehicles. A driverless car, on the other hand, is actively monitoring the environment around it and performing the actual functions of accelerating, braking, and navigating. Driverless cars are just now beginning to achieve some level of acceptance. The SAE defines 6 different levels of driving automation, from level 0, where the vehicle simply issues warnings and may intervene but is not doing any constant vehicle control, to level 5, where the steering wheel is completely optional. I have owned one of these level 2 to 3, let's say 2.5 vehicles, and I must say it does take some time to trust the system to perform safely at speed and in traffic. Based on some of the road conditions I've encountered, I'm not sure I can ever trust a completely driverless steering wheel optional vehicle. I must admit that while I'm no longer on a flip phone, I fall into the mature consumer designation mentioned previously, so perhaps I am not the appropriate consumer for a fully driverless vehicle. Traffic pattern monitoring. If we could send information relating to the current traffic we are encountering and receive information from other vehicles or from other traffic monitoring devices such as traffic loops and cameras, we could greatly reduce our travel times. We could use this information to suggest alternate routes in real time and balance traffic flow among these different routes. In 2014, Professor Carlo Ratti from MIT and others investigated the savings in emissions and fares we could achieve if we could implement a ride-sharing infrastructure among taxis in New York City. This has been tried before, but the algorithms, computing power, and mobile devices and applications were not yet ready for this, and this effort failed. Implementing vehicle pooling with shareability also allows us to manage and reduce traffic congestion. According to Dr. Ratti, recent advances in information technologies have increased our participation in sharing economies, where applications that allow networked real-time data exchange facilitate the sharing of living spaces, equipment, or vehicles with others. However, the impact of large-scale sharing on sustainability is not clear, and a framework to assess its benefits quantitatively is missing. For this purpose, we propose the method of shareability networks, which translates spatial-temporal sharing problems into graph-theoretic framework that provides efficient solutions. Applying this method to a data set of 150 million taxi trips in New York City, our simulations reveal the vast potential of a new taxi system in which trips are routinely shareable while keeping passenger discomfort low in terms of prolonged travel time. Today, speed limits on roads are static and are established based on estimated maximum safe speeds supported by a particular road. If we have real-time access to traffic information and the speed of that traffic, we can use mathematical models such as queuing theory to dynamically change the speed limits to achieve a better, more efficient traffic flow. If we consider the traffic flows to be queues and then reduce them to Markov chain constructs, we can easily solve for the best speeds and routes. The use of Markov chains assumes that we can make traffic predictions based on the current state of traffic just as well as if we consider the past states or history of the traffic flow. It may seem counterintuitive, but a slower speed limit may result in a shorter travel time, even on the same route based on traffic or queue congestion. Optimal route is very similar and closely related to optimal speed. Just as dynamically managing speed can shorten travel time, so can dynamically changing routes. This could also be called route balancing. If we manage vehicle speeds, we can still gain efficiency by managing traffic flows among different routes. As mentioned before, we can monitor traffic flows and reroute traffic as needed along the optimal at that moment route. This could result in two vehicles in close proximity that are traveling to the same destination being routed over completely different routes to that destination. Ideally, they would arrive at the same time. We have primarily considered vehicle to infrastructure communication up to this point, but we also need to consider vehicle to vehicle communication. This should not and probably cannot replace conventional car to infrastructure communication, but it will enhance that by adding information from other vehicles. A few years ago, Professor Daniela Russ worked on a study studying the traffic flow on the island city-state of Singapore. The question she wanted to ask, or wanted to answer, was can you predict traffic flow based on taxi GPS data, loop detectors, intersections, and if so, what algorithms do you have to use? First, she looked at how does traffic flow on work days versus non-work days, rush hours versus non-rush hours. Where does the traffic originate? What is its destination? What routes are taken? And how does this affect planning and resource allocations? Taxis were used and GPS sensors were placed on the taxis to measure traffic speed and delays. Inductive loop detectors were used at intersections to measure traffic flow. The question then became, is a taxi sample biased or representative of general traffic? And if it is biased, is it consistently biased and thus correctable? Her goal then became to predict the general traffic flow using taxi data and the available set of loop detection data. The approach she took was to learn linear regression coefficients. She used the traffic flow equals m times taxi flow plus b. And the different time models used for the linear regression were day categories and hour categories. And then she strove to find the best time model with the most predictive power. At the end of the study, Dr. Russ concluded that taxi traffic is a biased sample of overall traffic, but the bias is consistent and easily correctable, even at the granularity of individual intersections, and even just using workday versus non-workday plus the hour of the sample. And she ultimately concluded that you could infer overall traffic from taxi traffic.
In this section, we are going to talk about connected cars, diagnostic and prognostic system. The purpose of this system is to collect data from different sensors installed in the car related to the health status of different parts and send it over the internet to the backend application located in cloud for performance management. The cloud system has algorithms to detect various issues in the car and send real-time notification or alerts to the service center, dealership, or actual driver of the car. The various scenarios where connected car diagnostic and prognostic services are useful are as follows. Predicting and scheduling a service. Connected car can predict maintenance and performance management, appointment scheduling by collecting status updates on vehicle components, valves, brakes, through onboard sensors. The data is also shared with OEM suppliers to predict component demand with dealers and repair shops for preemptive maintenance. Real-time alerts. The data can enable automakers to monitor vehicle systems in real time, deliver alerts and dashboard warnings, and detect issues down the road while the car is in motion. Fuel consumption for eco-friendly driving. Fuel consumption messages. It sends warnings to the driver if the tires have low pressure or if the fuel efficiency is deteriorating or the wheel alignment is off. Connected car has various benefits such as avoiding downtime. Servicing and maintaining car ahead of time prevents expensive downtime later. Insights reduces cost. Having more insights about your car can reduce cost. Extends car life. Proper maintenance can further extend car's life. Advantages: reduction in service and maintenance costs as only parts which need to be replaced are taken care of. Real-time alerts of possible part failure, thus avoiding breakdown and costs associated with outages. Analytics and reporting dashboard can be used to view how the car is performing over different periods of time and in different locations. Drivers' driving habits can be analyzed and appropriate actions can be further taken. Tours and cab providers can manage the fleet better, thus maximizing profit.
This was CSCI E78's Team 3A's case study, The Connected Car.